Welcome back, geologists. Professor Rood here, going to discuss radioactive decay. This is video 4 for chapter 9, Geologic Time. Let's start with a review of the atom. Remember, the nucleus contains protons and neutrons. That's where the mass of the atom exists. Protons are positively charged, neutrons are neutral. The electrons are very small in mass compared to protons and neutrons. However, they definitely have a charge, and that is negative. The atomic number for a chemical element tells you how many protons is in the nucleus. The atomic number is the fingerprint of the element. The atomic number for a specific element never varies. For example, carbon always has 6 protons. However, it can have a varying number of neutrons. Another number we can discuss is called the mass number. That is a whole number. It is the number of protons and neutrons in the nucleus. An isotope for a particular element is a variation in that element. It varies in the number of neutrons and therefore mass. The number of protons never varies for a particular element. This is how we write a chemical symbol. Here's our chemical, and here we're our element. Here we are looking at carbon. The atomic number is the lower left number, tells you how many protons, which tells you what element you have. And above is the mass number. In order to calculate the number of neutrons carbon has, you simply take the mass number and subtract the atomic number. So in this case, carbon 12 has 6. What's that for a 6? 6 neutrons. 12 minus 6 is 6. In order to determine the numerical or absolute age of a rock or mineral, radiation must be used, or radioactive elements, I should say, need to be used. A substance, an element that is radioactive, simply means that its nucleus is unstable for a variety of reasons. It may be unstable due to its size. It is too large, for example. It may be unstable because there are too many protons compared to the number of neutrons, or vice versa. Or it simply may have too much energy to be stable. Whatever the reason is, it will decay and become something slightly more stable. And we're going to define, in this case, just 3 types of radioactive decay. The first one is alpha decay. In alpha decay, an alpha particle, which is 2 protons and 2 neutrons, is emitted from the atom. The reason that a nucleus undergoes alpha decay is it's too large. What better way to become smaller than to get rid of 2 protons and 2 neutrons? The mass number will be reduced by 4, and the atomic number is reduced by 2. Let's take a look at this. Let's look at alpha decay. We're starting with an unstable parent nucleus. I'm going to use the element uranium-238. The 238 tells you its mass number. That is the number of protons plus neutrons in the nucleus. All uranium has atomic number 92 protons. If we alpha decay a U-238 nucleus, our mass number decreases by 4, so it becomes 234. Our atomic number decreases by 2, it becomes 90. 90 is the atomic number that tells us what element we have. We look at a periodic table, and element number 90 is TH, which is thorium. So when U-238, if it were to alpha decay, it would become thorium-234. Here is an image of the process. Beta decay is another type of radioactive decay. A beta particle is simply an electron that gets ejected from the nucleus. The reason a nucleus would undergo beta decay is because it has too many neutrons compared to the number of protons. So the neutron changes into a proton and ejects a beta particle, an electron. As a result, the mass number remains unchanged. However, the atomic number is increased by 1. We have one more proton now. Let's take a look at that in visual. Here is our example, beta emission. I'm going to use uranium-238 again. Remember, 238 is its mass number. And so with beta decay, mass number stays the same. So we're going to still be at 238. But our atomic number, 92, goes up by 1. And so it becomes 93. If we look at the periodic table, the element that is numbered 93 is neptunium, Np. Here is a visual, protons and neutrons. The neutron changes into a proton and in the process spits out a beta particle. As a final example, we're going to use electron capture. It's just what it says. An electron gets captured. And the reason that a nucleus undergoes electron capture is because there are too many protons compared to the number of neutrons. So the proton captures the electron, which changes it into a neutron. Once again, mass number stays the same. However, this time the atomic number goes down by 1. Let's look at this as an example. This is our electron capture example. We're going to use uranium-238 again. Mass number stays the same, 238. And the atomic number goes down by 1, so it goes from 92 to 91. And element number 91 on the periodic table is Pa, protactinium. Here is the visual. The proton captures the electron here, converting it into a neutron. We use the term parent and daughter products to describe radioactivity. The parent is the unstable radioactive isotope you're starting with. What that parent decays into is called the daughter product. Knowing the ratio between how much parent versus daughter isotopes are present in a rock is used to determine its numerical or absolute age. This is an image showing the decay chain for uranium-238. So we start up here with U-238. Red arrows indicate alpha decay and blue are beta. U-238 undergoes alpha, turns into thorium-234, and then we do a beta decay, alpha, 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 all the way down here. And finally, when we reach lead-206, it doesn't decay anymore. That's because lead-206 is stable. It is not radioactive. So the process stops then. Please note on this diagram as well, this is atomic mass or mass number plotted against the atomic number. Radiometric age dating is the technique used to determine the age of rocks. Half-life is the amount of time required for half of the radioactive parent to go away, to decay away into their stable daughters. Let's look at a visual of this. This axis is the percent of atoms present. This is the number of half-lives that have passed. The blue represents the parent. The red, the daughter product. So as the parent decays, the daughter is increasing. After one half-life, by definition, 50% of the atoms of the radioactive substance has decayed. One half-life, 50% of the parent is gone. That leaves 50% of the daughter remaining. Let's go to 2 half-lives. We have to cut the 50 in half again, so 25 atoms of the parent remains, and 75 of the daughter. We have to add back up to 100%. Let's go to a 3rd half-life. That would only leave 12 and a half, we can round it to 13 atoms, and 87 and a half atoms of the daughter product, and so forth. And we can technically continue to have to infinity. Eventually, though, there becomes a point where there are not enough parent atoms left to determine the age of that rock. In our next video, we're going to take a look at some particular pairs of isotopes that are used in the geology world to determine numerical or absolute ages.